This video is part 2 in our video series for section 9.5 using determinants and Cramer's rule. In our last video we looked at evaluating systems of equations in two variables, solving for our second order determinants and using Cramer's rule. In this video we are looking at systems of equations, or a system of equation in three variables, determining third order determinants and then using the third order determinants and Cramer's rule to solve for the variables. Remember in the first video when we were solving for second order determinants, we created a 2x2 matrix, and then what we wanted to do to solve for the determinant is find the product of the diagonals. So A1 times B2 and A2B1. Find the products of those diagonals and subtract them to solve for our determinant. Now when we look at a system of equations in three variables, we create a matrix, or a matrix, that is 3 by 3. So now we have 3 rows and 3 columns. Now remembering the pattern from a 2 by 2 where we find the products of the diagonals and then subtract the product of the opposite diagonal, we're going to use that same pattern to solve for third order determinants. However, this time we have more than 2 diagonals to work with. So let's look at the pattern. We're going to take this middle diagonal. So here's our middle diagonal, and that's going to be our first product. We're going to multiply together A1, B2, and C3. Then we're going to take our second diagonal going left to right, which is B1 and C2. So B1 and C2, and if you can imagine that that actually also includes A3. So this diagonal wraps around and grabs A3. So our next product is going to come from B1 times C2 times A3. That's the second diagonal going down left to right. And then our third diagonal is going to be this C1 and include A2, B3. So there's all of our diagonals that are going left to right. We then are going to do the opposite diagonals. So I'm going to change my pen color. Next, we're going to find the products of A3 times B2 times C1, which is right here. And because our diagonals are going the opposite direction, we're now going to subtract them. So A3, B2, C1. And then our next diagonal is here, B through B3, C2, and that is going to include A1. So that's right here. And then our last diagonal is this C3, A2, B1. So we find the products of all of our blue diagonals, let's say, the ones that I've circled, and then we're going to subtract from that the sum of the products that are going the opposite direction. So we're still working on the same pattern that we did before, but now it's expanded out because we do have this 3 by 3 matrix. Imagine the creativity of the mathematicians that discovered Cramer's rule, to be able to see the patterns in the products of the diagonals and to subtract those products to find constants that then could be used to solve systems of equations. I find that amazing. Cramer's rule was presented in the 1700s, and the two mathematicians that worked on Cramer's rule were in the 1700s were these two gentlemen. Gabriel Cramer, who the rule is named after, and Colin Maclaurin. Now, Colin Maclaurin, history says, was the first to actually work out these patterns, and then Gabriel Cramer came after him. What I find very interesting is that the works of these two gentlemen were built upon by another mathematician, Olga Tosky-Todd. And Olga Tosky-Todd was well known for her work with matrix theory, in particular the computational stability of complex matrices. And if you look her up on Wikipedia, it's quite interesting. She used matrices to analyze vibrations of airplanes during World War II at the National Physics Laboratory in the United Kingdom, and she became the torchbearer for matrix theory. During this time, she wrote several articles that were published by the Ministry of Aircraft Production in London. Now, she found that the theories of Gabriel Cramer and Colin Maclaurin, this Cramer's rule, worked for 2 by 2 and 3 by 3, but anything higher than a system of equations in 3 variables, then Cramer's rule became unstable. Another fun fact is that when she was a young mathematician, she was hired by a group of German mathematicians to find and correct the many mathematical errors in the works of David Hilbert. And the reason why they wanted her to do that is that for David Hilbert's birthday, they wanted to give him a book of all of his mathematical errors corrected, and she was put to work on that. So that was one of her early jobs as a mathematician, but her biggest claim to fame was really her theories on matrices. Well, that's enough of a history lesson. Let's go back and use this third order determinants to show how we can solve for variables x, y, and now z using Cramer's rule. So here's the general pattern of a third order determinant. We're going to take the diagonals, the blue diagonals, we're going to find the products, and we're going to subtract from that the products of the red diagonals. And this will give us the value of the determinant. Now this can take up a long time, so I'm going to show you a shortcut, and the shortcut is called minors. And minors are a short way of finding a determinant without having to go through the process above. So follow along with me as I show you this shortcut. Basically, we are taking a 3 by 3 matrix and turning it into a 2 by 2 matrix. And how we do that is we take the first element in our matrix, which is A1, and then we're going to multiply that by the determinant for a 2 by 2. And how we find out the 2 by 2 is we cross out the column and the row that A1 element is in, and then the 2 by 2 matrix that we have left over is going to be used to find our determinant here. Next, we're going to subtract the element A2, and here is element A2, and we're going to subtract A2 times the determinant of a 2 by 2 matrix, and again, to find the 2 by 2 matrix, we're going to cross off the column that element A2 is in, and the row that A2 is in, and that's going to leave us with B1, C1, and B3, C3 for our 2 by 2 matrix. And then lastly, we are going to add the product of A3 and its minor. So these 2 by 2s are all called minors. So this is A1's minor, this is A2's, A2's minor. Let me try that again. A2 and the minor of A2, and then A3, and we're going to look at the minor of A3. So here is A3, and to find its minor, we're going to cross off the row and the column that A3 is in, and that's going to leave us our minor, which is this 2 by 2. So it's going to be B1, C1, B2, and C2. Do note that we have that we're subtracting this product and we're adding this product. So it's very important that you have your signs correct in this case. So you need to make sure that you watch for those. But this is going to be a shortcut for finding the determinants for a 3 by 3. So instead of doing a 3 by 3, you're now just doing 2 by 2s. Okay, let's put this theory into practice. Here we have a system of equation in 3 variables. We have our variables x, our variable y, and our variable z. And the first thing that we want to do is we want to create a matrix based on this. So we're going to take the coefficients of the first row, which is 3, -2, +1, and 16. And then the second row, 2, +3, -1, and -9, and then 1, 4, 3, and 2. So this is our original matrix for this system of equations in 3 variables. Now from this matrix, we want to find our determinant D, our determinant X, our determinant Y, and our determinant Z. And we're going to use minors to help us solve for each of these determinants. So let's go ahead and solve for determinant D by itself. So determinant D only uses this part of the matrix. And here is the matrix for D. And now we're going to solve the determinant for D using minors. So the first thing we're going to use is A1, which is 3, plus A1's minor, which again, remember, we're going to take the row and the column out, and that's going to leave us with this 2 by 2 here. And there's the 2 by 2. Then we're going to subtract A2, which is here, and its minor, which is going to be this row and this row gone, so we'll be left with 2, 1, 4, and 3, and that's a -2, so make sure that you're careful when you transcribe that you include any signs. And then we add A3. And A3 is right here in this element A3, so that's going to be adding 1 and its minor. And A3's minor, again, if we were to cross out its row and cross out the row and cross out the column, we'd be left with -2, 1, 3, and -1 right here, and that's what we have here. Now I'm going to go ahead and find the determinants for just these 2 by 2 minors next. And again, when we're finding the determinants for 2 by 2s, we're going to multiply the diagonal to get the products, and then we're going to subtract. So I've gone ahead and done the determinants for the 2 by 2s. So 3 times the determinant of the 2 by 2s, so I'm going to do 3 times 3, subtract -1 times 4. Then I'm going to do -2 times 3, subtract 4 times, little slight error there, 4 times 1. And then lastly, -2 times -1, subtract 3 times 1. And then of course in front of these are our A1, A2, and A3 elements. And then simplifying within the brackets, it's going to be 3 times 13, that's the determinant for the 2 by 2, subtract 2 times -10, that's -10 is the calculation for that determinant, and then plus 1 times -1, which is the difference for that determinant. And then simplified again we get 39 plus 20, subtract 1, and then lastly, D is equal to 58. So we have the first determinant constant figured out. Only 3 more to go. Next, we're finding the determinant dx. So first of all, we need to create the 3 by 3 matrix for dx. When we're doing the dx determinant, the first thing that we want to do is we want to just take out our first column, that's our x values, and then what we're going to use is we're first going to write down our constants, which are 6, -9, and 2, and then we're going to use our column 2 and column 3 for the rest of our 3 by 3. So here's the 3 by 3 that we are using. And next we are going to use minors. Now before we used A1, A2, and A3 as our coefficients for our 2 by 2s, but I want to let you know that it really doesn't matter what column you use. For instance, I'm going to use 1, -1, and 3 because it's much easier to multiply a 2 by 2 by 1 than it is by 16. So feel free to use whatever column works the best, but when you're working within a column, you have to make sure that you stick within the column. So actually I'm going to use C1, C2, and C3 as my coefficients for doing my minors. So here I go. I'm going to use 1, and then its minor is going to be -9. Need a little bit more space. Is going to be -9, 3, 2, and 4. Subtract my next one, which is -1. Put that into brackets so that I include both of the negatives here. And that's that one there. So if I write it out like this, that's going to give me 16 and -2, 2, and 4 as its minor. And then I'm going to add my third one. And if I were to take out that column and that column, I'm left with 16 -2, -9, and +3. Now just to save time, I've gone ahead and I have written out the determinants for the 2 by 2 in each of the cases of the minors. So we'll have 1 times the diagonal of -9 times 4 subtract 2 times 3, and then 16 times 4 subtract 2 times -2, and then this last one for 3 will be 16 times 3 subtract -2 times -9. What this simplifies to, when you figure out inside the brackets and then multiply by the coefficients in front, you'll get -42 for the first minor plus 68 for the second minor plus 90, and that gives us dx is equal to 116. So we have dx is equal to 116, and we had the original d is equal to 58. So we're slowly building up. And to save a little bit more time, here are the 4 solutions for determinant d, dx, dy now. So this is my dy and my dz. It's important that you see how we create the original 3 by 3 for dy and dz. So for one of the things that you'll notice is that the original matrices for D is just your X, Y, and Z column. And then when you're doing your determinants for X, Y, and Z, what you do is you replace your column for X with the constant. So here is my x column, and I put in the constants 16, -9, and 2 for my x column and left my y and z column. For my determinant y, I replace the y column with my constants 16, -9, and 2 and leave my x and my z columns as is. And then for my determinant z, I take the z column again and I replace with my constants of 16, -9, and 2 and leave x and y. So that's an easy way to get your 3 by 3 matrix for each of dx, dy, and dz. And you can see how we get our determinants. Again, what column you use as your coefficients, I would suggest use the column that has the most ones. So in dy, they use 3, 2, and 1. I would probably go back and use 1, -1, and 3 if I were doing it, but it doesn't matter. And again, for dz, they did 3, 2, and 1. But I think I would have stayed with that one as well because it is the least numbers. So it's harder to multiply with larger numbers. Nicer to go with the column that has the smallest number values in it. So let's look at using Cramer's rule now for solving for our x, y, and z variables. So we're going to use Cramer's rule to solve for x, y, and z. So x is going to be our dx divided by d, which was our dx, our determinant x was 116, and our d value was 58, so x is going to be equal to 2. Y is going to be determinant y over d, which is equal to 174 over 58 is equal to -3, and our z variable is determinant z over d, which is equal to 232 over 58 is equal to 4. So the solution to the system is going to be x is equal to 2, y is equal to -3, and z is equal to 4. And that's our solution set for our system of equations in 3 variables. That's it for section 9.5. I thank you for watching. And if you have any questions, please do post to the Q&A discussion for Unit 1. Bye for now.